In introductory programming courses, instructors use in-class programming exercises a lot to help students practice their coding skills and reinforce the concepts they learn in class. However, monitoring students' progress can be challenging for instructors. In a single problem, there is a variety of reasons that students might not be able to pass the unit test. To identify students' misunderstandings, instructors need to read their code in order to gain more insight into their intentions because misconceptions tend to be implicit and abstract. In addition to that, students would solve a problem using different approaches. While students are working toward a final solution, they may be at different stages of solving a problem. Some students are close to a final solution where they only need to make a minor code change, while other students have no clue how to begin. Due to the nature of programming exercises, it can be particularly challenging in large classes. In large classes, instructors face large amounts of repetitive questions and lack TAs to scale support for students. Therefore, instructors must develop effective strategies to surface students' struggles in in-class exercises. To address these issues, researchers have developed systems for instructors to view students' code in programming exercises. For instance, Overcode clusters correct code submissions that perform the same computation and provides a visualization of the clusters by grouping submissions into bins. The downside is that Overcode only announces the final submissions and does not summarize history versions and how students come up with the solutions. Another system is CodeOpticon, where each learner's progress is summarized in a tile in real time, and the instructors interact with a dashboard consisting of a list of tiles. It helps instructors give students support in real time by watching students editing and debugging and chatting with them. However, this tool is limited to small-scale sessions where instructors have the bandwidth to provide one-on-one feedback. It is also challenging to monitor the history versions of the whole classroom. To better understand how existing practices and tools work in conducting in-class programming exercises, we interviewed 6 instructors. In the interviews, we explored the instructors' needs and challenges in in-class exercises. The results showed that monitoring students' coding progress in real time is necessary. It helps instructors surface students' struggles, give feedback, and make plans for the remainder of the class. We also found challenges such as visualizing students' progress at different granularities, validating students' progress at scale, and providing tailored feedback on progress at scale. Led by prior work and our interviews with instructors, we proposed a new design of mapping students' progress onto a 2D map. The design aims to facilitate monitoring progress in real time in in-class exercises. On the 2D map, there is a start point where students have empty editors, and there's the destination where all the correct solutions are. As students working toward a final solution, instructors can see the paths in between. For example, students can start from the bottom left corner, moving toward the right side of the map, where the correct solutions are. While they're working toward a final solution, students who have similar errors will be close on the map. Some students will be very close to the right side of the map, only needing minor changes, while some students are at the far left side, having no clue how to begin. We introduced VizProg, a system that explicitly encodes human understandable meaning to the 2D space. VizProg works in real time at the keystroke level. VizProg's user interface consists of 3 main panels: the overall class progress 2D map view, a solution-centered view, and a progress detailed view. In the 2D map, student status is represented as a position. Large colored dots represent where students are. Blue dots represent students who have solved the problem successfully, while orange dots represent students who have not yet found a solution. The small gray dots represent versions of code that students have tried but not have since moved on. The gray lines represent trajectories between 2 consecutive versions of code. In the 2D map, the 2D Euclidean distances encode similarities in students' code. The vertical positions encode how students approach the exercise. The horizontal position represents how close students are to a correct solution. The trajectory represents how student status changes over time. Now I'm going to show you what that looks like in a screen recording where more than 100 students are working on an in-class programming exercise. Let's take a look at an example of 3 students solving a problem. The problem is to create a list ranging from 0 to 40 and calculate the summation of the list. Instructors will see students' positions changing on the map as they type. As the 3 students working toward a final solution, their dots are moving from left to right. The student in orange finds the correct solution quickly. The student in blue ends up being close to solution 24. The student in purple is struggling and very far from the correct solution. VizProg allows the instructor to inspect the submissions from all the students who arrived at the same solution by clicking a solution. The list contains 3 main sections: statistics related to the solution, a list of IDs of students who are close to the solution, and a list of submissions made by these students. Instructors can click the student ID to view the trajectory and code history of a specific student. The Progress Detailed view displays all the submissions made by the student throughout the history of the exercise. Instructor can also navigate students' progress at different granularities. To examine the progress of groups, instructors can crop a region on the 2D map to see the submissions only within that region. To assist users in identifying common misconceptions, submissions are listed by error type frequency in descending order. By resizing the overlay or dragging the overlay on the 2D map, the user can view real-time updates on the progress detailed view of the selected region. For individual progress, users can either search by student ID or click a student ID on the solution-centered view. We compared VizProg to Overcode in the evaluation study. To ensure a fair comparison, we augmented Overcode to adapt it for real-time use. Participants watched a replay of approximately 110 students solving a programming exercise using VizProg and Overcode. After the replay, they answered quiz questions to evaluate their understandings of students' progress and approaches. The results showed that participants understand students' problems more accurately than with the baseline system. They tend to describe problems more specifically by pointing out the parts that made the code incorrect. Participants understand students' issues faster in live settings using VizProg. It also takes less context switching in live settings using VizProg than the baseline system. It takes less effort for participants to validate students' progress. Using VizProg, participants quickly form a strategy to decide who to give feedback to. More details can be found in the paper. We have 2 main takeaways from the studies. First of all, VizProg is intuitive to use. The movement from left to right tells that students are making progress. Examining progress at different levels on map is straightforward. Second, trajectories in VizProg ease the reasoning process. The dynamic and paths provide visual guides to reasoning about students' normal and abnormal behavior. In conclusion, we provide a better understanding of the needs and challenges that instructors face when monitoring students' in-class coding exercise. We propose VizProg, a system that encodes students' approaches and progress on 2D map view to facilitate monitoring students' progress in real time. We provide evidence showing that VizProg can help identify more misunderstandings and important behaviors in coding exercises than a baseline system.